In this video, I'll show you how to make your own smart LED lighting system using an Arduino. By smart, I mean it reacts to some sort of sensor, anything more advanced than a basic light switch. The great thing about Arduino is that it's compatible with tons of different sensors, so you can make your LEDs react to pretty much anything you want, like distance, motion, sound, or ambient light levels. I'm going to demonstrate 5 different sensors in this video: a passive infrared or motion sensor, an ultrasonic distance sensor, a potentiometer, a microphone, and a photoresistor or light sensor. I'll show how you can use each one to control an analog RGB LED strip. We also have more detailed tutorials about each one of these individual parts in our Arduino tutorial playlist linked in the video description. Let's start with a quick overview of the wiring for the RGB LED strip. This is an analog strip, meaning that the LEDs are not individually addressable. All of the LEDs on the strip will always appear the same color. You can buy digital, individually addressable LED strips, but the code for those is different. The example code for our project, which you can find linked in the description, is going to be for the analog strips. These strips have 4 connections, one for each color LED, and one for 12-volt power. You can buy them pre-terminated with wires, or you might have to solder the wires on yourself. And you can also cut them to length along these lines, so don't cut in the middle in between the LEDs, but every few LEDs along the strip, there's going to be a section where you can cut them if you don't want the whole length of the strip. On the breadboard, we have 3 N-channel MOSFETs, or power transistors, that are going to control the current through the LED strip. Each one of those MOSFETs has 3 pins going from left to right: the gate, drain, and source. The gate pin is going to be connected to a PWM pin on the Arduino. Those are the pins with the little squiggly line next to them. That will allow you to use the analog write command to control the LED's brightness. The drain pin is connected to the wire that controls that respective LED color on the LED strip. And then the source pin is connected to ground. And you're going to repeat that for all 3 MOSFETs. And again, that was just a quick overview. We have a much longer, more detailed video about the wiring for these LED strips in our playlist linked in the description. So if that was too fast, make sure you go check out that video. We also have an external 12-volt power supply. These LED strips run off of 12 volts, so you cannot power them directly using the 5 volts from your Arduino. When connecting that external power supply to your breadboard, you can see I have a barrel jack adapter here that allows me to plug the power supply into this adapter that lets me connect jumper wires to these screw terminals and then plug them into the breadboard. I also have the positive wire running to a power switch here that I can use to turn the 12-volt power on and off. When doing that, you want to make sure your entire circuit has a common ground. So I have the ground wire from the power supply going to the ground bus of the breadboard, which is connected to the ground bus on the other side and is connected to the Arduino's ground pin. So the whole circuit has a common ground, but you want to make sure you do not short circuit the 12 volts from the power supply to the 5 volts from your Arduino. You'll note that I do not have a jumper wire connecting the power buses on the opposite sides of the breadboard here, so I have my power buses isolated. I have 12 volts over here for the LED, and I have 5 volts over here for any sensors that I'm going to connect in the future. You can see there's a few leftover wires here from a sensor that I had connected earlier and forgot to remove before I filmed this part of the video. But again, very important not to short circuit 12 volts to 5 volts or you can damage your Arduino. After you have your LED strip connected and wired properly, you can test it just by running code that makes it automatically fade through different colors. This lets you test to make sure that the LED strip is connected correctly before you worry about any sensors. Switching over to the computer to take a brief look at the code to do this automatic fading, which you can download from the link in the description, and we go over in more detail in our video about setting up the LED strip, so I'm not going to go through it line by line here. But the basic idea is that you use the analog write command to set red, green, and blue values for the LEDs. Each one can be between 0 or off and 255, which is full brightness. And you can mix and match these values to create different colors. So for example, you can use for loops to change just one value at a time to transition between different colors. For example, going from red, which is an RGB value of 255.00, to yellow, which is 255.255.0. You increase the green value one at a time while keeping the other two values constant, and you can then repeat that to transition between different colors. Again, I'm not going to go through this code line by line here. You can download it from the link in the description. After that, you're ready to start making the LED strip react to different sensors. The first one we will show is this passive infrared or PIR motion sensor that detects motion using body heat. Again, we have a complete tutorial all about these PIR sensors linked in the video description, but a very quick overview here for now. These sensors are pretty simple to connect. They just have 3 pins, plus, minus, and out. So plus is going to go to 5 volts from your Arduino, minus is going to go to ground, and out is going to go to one of your Arduino's digital pins. These sensors usually have male header pins attached to them, so you can connect to them with male to female jumper wires. You slide the female end of the jumper wire onto one of the male header pins, and then the male end of the jumper wire is going to plug into your breadboard or your Arduino. Looking at the code to do this, which again you can download from the link in the description, but I will go through in more detail here. First, we define pins, 1 for our sensor, which is connected to one of the digital I/O pins, and 3 for the LED control, red, green, and blue. We then define variables we will use for the LED brightness and a variable for the sensor state. In our setup function, we set the LED pins as outputs and the sensor pin as an input. We also initialize serial communication, so we can use that to print out sensor values or debug, and have a pretty long delay at the beginning of the program. Since these PIR sensors are very sensitive, that gives you time to boot up and turn on your Arduino and then get out of the way so the sensor doesn't just detect you immediately because you were already moving next to your Arduino. You can make that delay longer if you need to. In our loop function, we use the digital read command to read the sensor pin to get the sensor state. And then we have an if-else statement that tells the LEDs what to do depending on whether the sensor state is high or low, meaning whether or not it detects motion. So if the sensor is low, so no motion is detected, we set the color to green by setting red and blue to 0 and setting green to 255. Else, if the sensor is high or it detects motion, then we set it to red, so you can sort of think of this like an alarm, by setting red to 255 and setting green and blue to 0. Of course, you could change the colors here or program any other behavior you want, like flashing on and off for the LEDs. Finally, we have a short delay in the loop before we take the next reading. Next, we have the ultrasonic distance sensor, which emits a burst of ultrasonic sound and measures how long it takes that sound to reflect back to the sensor, which allows you to calculate the distance to an object. These sensors come in slightly different varieties. Some have 3 pins and some have 4. Again, these are male header pins that you can connect to your Arduino using male-female jumper wires, and you will need to read the labels to see what the pins are. They will usually have a ground and 5-volt connection, and then 1 or 2 signal pins. Some sensors use a single pin for both the trigger signal and measuring the response. Some sensors break that out into 2 different pins. As always, we have tutorials for both of these sensor types linked in the description of our video. Looking at the code, this program is based on the example code for the ping sensor available in the Arduino IDE under File, Examples, Sensors, Ping, but modified slightly for the HCSR04, which is a different, much cheaper ultrasonic sensor that uses 4 pins instead of 3. Again, you can find tutorials for both linked in the video description. In this code, we define constants for the 2 pins we will use to control the sensor, 3 LED control pins, LED brightness values, and then 2 minimum and maximum distance variables, which I will talk about a little more later. In our setup function, we set inputs and outputs for the appropriate sensor control pins and LED pins, and then again we also initialize serial communication so we can use that to print out sensor values. Then we get a bit into the example code for controlling the sensor, where we define some variables for the duration of the ultrasonic pulse, the distance in inches, and the distance in centimeters. The code then sends a trigger pulse by setting one of the output pins high briefly. This sends a pulse to the sensor and activates it to tell it to emit a burst of ultrasonic sound. And then you read the echo pulse, or the return pulse, that tells you how far away an object was. It's actually measuring how long it took the sound to bounce back to the sensor, And then the example code has functions to convert that time to distances in inches and centimeters based on the speed of sound. Again, we cover that a little more in the tutorial videos for the specific sensor. It's just built into the example code, so you don't really have to worry about writing that yourself. Now, here is the interesting part of the code that is not part of the example program. We use the Arduino map function, which maps values from one range to another range to convert that distance in centimeters, so this is where I'm using those min distance and max distance variables from before, to RGB values. And you need to use the map function to convert that range because the distance in centimeters you're measuring is probably not going to go between 0 and 255. You might have some other, for example, smaller range if you're just waving your hand back and forth in front of the sensor. So I set this between 0 and 20, but you can change these values. It's a little more intuitive to look at what I'm doing for green here. So what this is going to do is map when the minimum distance, or the distance measured, is the minimum, or 0 centimeters, then the output green value is going to be 0. But when the distance is 20 centimeters, then it's going to turn green up to full brightness and set this to a value of 255. For red, you will see that I have those values reversed. So red is going to be 255 when I'm at the minimum distance, and then as the distance increases, the red value is actually going to go down to 0. So you can do an inverse mapping or negative slope with the map function if you just reverse these two values. And what that does when I then use the analog write command to set my LED brightnesses, as you saw in the video clip earlier, is it lets me crossfade between red and green. So when my hand is very close to the sensor, then it's going to be red because my red value will be high and my green value will be low. As my hand gets farther from the sensor, the red value will go down and the green value will go up. This is just one example of what you can do. You can change this part of the code to do whatever you want based on the distance. We then have some serial print commands to print out the distances and the red and green values, and then a short delay before we take the next reading. And then outside of our main loop, there are those functions that come with the example code to convert time in microseconds to distance in inches or centimeters, but you don't need to edit these. Next, we have the humble potentiometer, which is simply a knob you can turn to control the LED brightness or fade between different colors. Potentiometers have 3 pins, so you put those pins into 3 adjacent rows on your breadboard. The 2 outer pins are going to go to 5 volts and ground, and the middle pin is going to go to one of the Arduino's analog inputs. Now, when you turn the potentiometer, the voltage on that middle pin is going to change, and you can read it with the Arduino's analog read command. The code for this is similar to what we just saw for the ultrasonic sensor, but reading the sensor itself is much simpler because it's just one line. So again, we define our pins, 3 for controlling the LEDs and 1 for the sensor, which is going to go to one of the analog pins this time. We then define variables for the red, green, and blue values and the sensor or potentiometer value. In our setup function, we set our LED control pins as outputs, and in this case, I am setting green to 0 because I'm only going to control red and blue with the potentiometer, but again, you could change that depending on what you want to do with the colors. In the loop function, it is then just one line to read the sensor, just the analog read command on the pin we have the potentiometer connected to. And then again, we are going to use the map function to convert our sensor value, which goes from a range of 0 to 1023 with the Arduino Uno's analog input pins to the range of 0 to 255 that we need for the analog write command. And again, I am doing a crossfade where I have one of these reversed, so as I turn the potentiometer, red is going to go up and blue is going to go down, or vice versa if I turn it the other way. I then write the values to the LED pins using the analog write command to control the brightness. Again, this is just one example of what you can do. You can change how the map functions work here to change which colors you control, or you can even add more potentiometers to do different things or have one control each color independently. Next, we have the microphone, which as shown here is just responding to loud sounds like a clap. It's not following voice commands. That is a topic for a different video, but we do have a series on voice control linked in the description. Microphone breakout boards like this one are commonly available for the Arduino. They contain the microphone itself and some additional amplification circuitry because the voltage output directly from the microphone is very small. So amplifying it to a 0 to 5 volt range makes it easier to measure it using one of your Arduino's analog input pins. Like many other sensors, these have 3 labeled pins, one for ground, one for power, which is 5 volts from your Arduino, and one for the signal out, which is going to go to an analog input pin on your Arduino. Again, these have male header pins, so you can either stick them directly into the breadboard and then connect to the Arduino with jumper wires, or use male-female jumper wires to connect the microphone directly to your Arduino. Looking at the code for the microphone, it starts out looking similar to what we had for the potentiometer because the microphone just goes to one of the Arduino's analog input pins. We then define our pins for the LED control, variables for the LED brightness, and a variable for the microphone reading on the analog input. Things then change a little bit because we are going to define a threshold variable that we will use later, and a variable to keep track of the LED state. As you saw in the video, we were cycling through 3 different colors. In our setup function, we then define our LED control pins as outputs and initialize serial communication for debugging and printing out sensor values. In our loop, we then use the analog read function to read the microphone pin, and here is where the code gets a little more complicated than what we had for the potentiometer. We have an if statement that checks if the microphone reading is louder or higher than the threshold variable that we sent earlier. So this is going to only detect sounds above a certain loudness. If that happens, then we are going to change the LED state. So we increment this variable by 1. But we only want to cycle through 3 states. We don't want that variable to keep increasing forever. So we also have another if statement in here that checks if the LED state is equal to 3, then it resets it to 0. This way, each time we detect a clap, the LED state is going to cycle between 0, 1, and 2, and then it's going to reset to 0. It's not going to keep going 3, 4, 5. We also then have a short delay inside this statement. That way, if we do detect a clap, we will wait a little bit before we take another reading so we don't accidentally switch states multiple times on a single clap because Arduino code runs really fast. So even though a clap seems really fast to you, that's enough time for the code to get all the way to the bottom of the loop function, all the way back to the top, and take another reading. So again, this delay, which you can adjust depending on the results you're getting, helps make sure that you don't accidentally transition multiple times on a single loud noise. We then have an if-else statement that sets the LED color based on the LED state variable. So if it is equal to 0, we're going to set the LEDs to red. If it is equal to 1, we're going to set the LEDs to green. Else, we know it has to equal 2 since we're resetting it when it reaches 3, so it can never be 3, 4, 5. Then we're going to set the LEDs to blue. So clapping in this case is going to cycle from red to green to blue back to red in a loop as you keep clapping, but again, this is just one example of what you can do. Once you have this code set up to detect the claps, you can then edit this part of the program to make the LEDs do whatever you want. Finally, we have the photoresistor or light sensor, which you can use to detect ambient light levels and make the LEDs react accordingly. For example, you can use these to make an automatic night light that turns on when it gets dark, or an auto-dimming sunset or sunrise alarm clock. Unlike most of the other sensors, you cannot plug the photoresistor directly into your Arduino. That's because it is a variable resistor, so its resistance changes with light levels, but the Arduino measures voltage and not resistance. So to measure a changing voltage, you need to build a circuit called a voltage divider by putting the photoresistor in series with a fixed resistor. One leg of the photoresistor then goes to 5 volts, the outside leg of the fixed resistor goes to ground, and the middle pin where the two are connected goes to your Arduino's analog input. Now, as light levels change, the voltage on that pin will change, and you can measure that with your Arduino. Again, that was just a very quick overview or crash course in photoresistors. We have a more detailed video all about photoresistors linked in the description of this one. The code for the photoresistor is similar to what we saw for the potentiometer and the microphone. We define a pin for our sensor input, which is one of the analog pins, and then the pins for controlling our LEDs. We also have a threshold variable that we're going to use to change the LED behavior based on whether the light level goes above or below that variable. Then we define variables for our LED brightnesses and our sensor reading. In the setup function, as usual, we define our LED control pins as outputs and initialize serial communication so we can print out the sensor value. In the loop function, we use the analog read function to read the sensor value from the sensor pin. And again, for the analog read command, that's going to give a number between 0 and 1023. We then print that value to the serial monitor so you can calibrate it. So you might need to run your program, open the serial monitor, and then test whatever you're going to do with your sensor, whether it's turning the lights on and off in the room, opening or closing the window blinds, shining a flashlight on it, to see what values you are getting for dark and light, and then adjust your threshold variable accordingly so it's somewhere in between those two extremes. We then just have a simple if statement that detects whether the sensor reading is greater than the threshold variable you have set. And in this case, I am just setting it to magenta if the sensor reading is above the threshold, else if it's below the threshold, I'm going to set it to cyan. But as always, you can change this part of the code to do whatever you want and make the lights behave as you want in different light levels. And this is just using an if statement to detect bright or dark, but you could use the map function, as we have seen in some of the previous examples, to have more of a continuous color change. Again, if you wanted to do something like a sunrise or sunset gradual fade instead of just on-off or swapping between two different colors, you could do that with the map function instead of an if-else statement like this. This video was an overview of just a few of the sensors you can use and a few different ways you can make the LEDs react to those sensors. But again, the great thing about the Arduino is that you can use whatever sensor or combination of sensors you want and program the LEDs to react however you want, so you can mix and match and design your own smart LED lighting system. Remember that for written instructions with downloadable example code for each one of these sensors, you can check out the link to our website in the video description. For over 1,000 other cool projects in all areas of science and engineering, check out our site, www.sciencebuddies.org.